Hello, welcome to the course on microwave engineering. Dear students, in the last video lecture, we have discussed about varactor diode. So, varactor diode is basically operated in reverse bias condition, and it is also known as a varicap because it shows the variable capacitance effect. Means if we change the reverse bias voltage, then capacitance of the diode is also changed. Hence, with the variation of the voltage, the capacitance is changed. Hence, it is known as a variable capacitor diode or simply varicap. Okay. So, if you would like to use the varactor diode, then we must have to operate the diode into reverse bias condition. Now, in today's class, we are going to discuss about another very important solid state semiconductor device, which is the tunnel diode. So first of all, what is tunnel diode? So tunnel diode is basically heavily doped p-n junction diode. Means its doping level is very high compared to our normal p-n junction diode, and it shows the negative resistance characteristics similar to गन डायोड. जैसे हमने देखा था कि गन डायोड में नेगेटिव रेजिस्टेंस कैरेक्टरिस्टिक्स थी, similarly tunnel diode also shows the negative resistance characteristic, and because of that the tunnel diode can be used as a amplifier and oscillator. So what do you mean by negative resistance? So if we increase the voltage, the current will decrease. Okay, and this tunnel diode works on the tunnel effect. Now this is the symbol of this tunnel diode. It has a two terminal, one is anode and another is cathode. Okay, and in symbol you can see there is a slight change compared to our normal p-n junction diode. Okay, in our normal p-n junction diode there is a straight line, but here there is a something different than our normal p-n junction diode. And if we talk about the origin of this diode, then Leo Esaki invented the tunnel diode in 1957. Hence, this is also known as a Esaki diode. And the material used for manufacturing this diode are germanium, gallium arsenide, and other silicon material. And very important to note, this diode shows the negative resistance in its characteristic. Now, if you look at the construction or doping level of this P and N type material, then compared to our normal p-n junction diode, the p-type material as well as n-type semiconductor material are heavily doped because due to the greater number of impurities, and because of this heavy doping, the width of the depletion layer is very narrow. तो बच्चों एक रूल है कि जितना डोपिंग ज़्यादा होगा डायोड में, उतनी डिप्लेशन लेयर की विड्थ कम होगी. अगर लाइटली डॉप डायोड होगा तो उसमें डिप्लेशन लेयर वाइड होगा, एंड हेवीली डॉप डायोड होगा तो उसमें डिप्लेशन रीजन नैरो होगा. सो टनल डायोड इज वेरी हेवीली डॉप डायोड, एंड बिकॉज ऑफ द हेवीली डॉप डायोड द विड्थ ऑफ द डिप्लेशन लेयर इज वेरी नैरो. सो एज कंपेयर टू normal p-n junction diode, tunnel diode has very narrow depletion width, and if the depletion width is very narrow, then by applying very small amount of voltage, it produces enough current through the diode. Okay, so you can see the width of the depletion region is very narrow over here. Okay, and because of this very narrow depletion region, very small amount of voltage is enough to create large amount of current through the diode. Now let's understand the working of this tunnel diode by considering the different cases. So if we consider the first case, that is zero bias condition or unbiased tunnel diode. If we do not apply any external bias, then what would happen in this tunnel diode? So in unbiased tunnel diode, means we have not applied any voltage to the diode, then due to the heavy doping of the diode, the conduction band of n-type material, so this is a conduction band of n-type material, basically overlaps with the valence band of the n-type material. This is the valence band of the p-type material. correct? And due to that, electrons from the n side and holes from the p side will overlap with each other because they will at the same energy level. So some of the electrons will tunnel from conduction band of n region to valence band of p region when some temperature is increased. Similarly, as the temperature increase, the holes from the valence band of the p-type material will also comes to the conduction band of the n-type material. So finally the net current will be 0 because the equal number of holes and equal number of electrons are moving from p to n as well as n to p. So if we see, then at 0 bias, the tunneling of the charge carrier is there, but current is 0 because there is the net tunnel current is 0 because equal number of charge carriers, equal number of electrons and holes are crossing from one region to another region in opposite direction. Now if we apply the small voltage to the tunnel diode, then if we apply the small voltage that is lesser than the built-in voltage of this depletion layer, then there is no flow of forward current through the junction, but minimum number of electrons from conduction band of the n-type material will start tunneling to the valence band in the p-type material, and this due to this small amount of electrons that crossing the junction from n to p, it will create very small forward bias tunnel current. It will produce small forward bias tunnel current when we have applied very small voltage to the tunnel diode which is less than the built-in potential of the diode. Okay, so जब तक आपने जो वोल्टेज अप्लाई किया है वो बिल्ट इन पोटेंशियल से कम है तो आपको बहुत ही कम करंट देखने को मिलेगा. There is a small tunnel current through the diode. Now if we increase the voltage applied to this tunnel diode, then if amount of voltage is increased, then number of free electrons generated at the n side as well as holes generated at the p side is also increased, and due to the voltage increase, the overlapping between the valence band and conduction band will also increase, means the overlapping of this conduction band of n type material and valence band of p type material is also increase. So more number of electrons are crossing the junction or tunneling through this junction and reaches to p type material, and because of that the current will or maximum tunnel current will observe. So maximum tunnel current flows when energy level of n side conduction band and energy level of the p side valence band becomes equal. Okay, correct? And if we increase the voltage, then overlapping will increase and ultimately it results in the maximum tunnel current through the diode. If we increase the voltage further, then what will happen? So if we increase the voltage, then it results in the slight misalignment of the conduction band and valence band, as you can see from the figure. Here there is a maximum overlapping between the conduction band of n-type material and valence band of p-type material. But as we increase the voltage further, the misalignment between the conduction band and valence band is increased. Still there is a small overlap between the conduction band and valence band, and electrons move from conduction band to valence band, and this will create small current. So ultimately, compared to previous case, the current will decrease or tunnel current start decreasing. So you can see from this figure, up to this point or at this point, the conduction band and valence band completely overlap, or they are at the equal level, okay, energy level, and because of that the maximum tunneling of the electron can taken place, and we are getting the maximum tunnel current. But as we increase the voltage further from this point, okay, then there is a slight misalignment between the conduction band and valence band, and tunneling of the electron from conduction band to valence band decrease and ultimately decrease the current. So current start decreasing. Okay, and again increase or large, if we apply the large voltage to the tunnel diode, then the tunneling current will become zero when applied voltage increase more to maximum value, because at this voltage the valence band and conduction band do not overlap. वैलेंस बैंड और कंडक्शन बैंड एक दूसरे को ओवरलैप नहीं करेंगे, और ओवरलैप नहीं करेंगे तो टनलिंग करंट नहीं मिलेगा. द करंट ड्यू टू टनलिंग विल नॉट बी टेकन प्लेस एंड द डायोड विल बिहेव एज अ नॉर्मल पीएन जंक्शन डायोड. यू कैन सी फ्रॉम दिस पॉइंट हियर द टनल करंट इज जीरो. द करंट ड्यू टू द टनलिंग ऑफ द इलेक्ट्रॉन फ्रॉम कंडक्शन बैंड टू वैलेंस बैंड इज जीरो, बट in this region the tunnel diode behaves as our normal PN junction diode. Okay, so if you look at the VI characteristics of tunnel diode, you can find one region, okay, in which as we increase the voltage the current decrease, and this region is known as a negative resistance region, which is almost similar to the what we discuss in gun diode. And because of this negative resistance characteristics, this tunnel diode is utilized for generation or as a oscillator and amplifier. So due to the forward biasing and because of the heavy doping, the conduction happens in the diode and the maximum current is denoted by IP, which is known as a peak current. Okay, and corresponding voltage is known as a peak voltage, that is VP. Okay, but as we increase, as we mention here, as we increase the voltage further and further, then diode current start to decrease. Okay, as we apply the more amount of voltage. Okay, in the point at which the current is minimum is basically known as a valley point, and corresponding current is known as a valley current, IV, and that voltage is known as a valley voltage. Okay, so the small minimum value of current that is flowing is IV, that is known as a valley current. Okay, so between point A and B there is a negative resistance region, and if you would like to operate the diode as an oscillator, we must have to operate the diode in this region. Okay, and after this point our tunnel diode will behave like our conventional PN junction diode. So up to this voltage, okay, it behaves as a tunnel diode because the current is flowing due to the tunneling of the electrons or charge carriers from one region to another region. But after that there is a no tunneling of the charge carriers across the junction, and diode behaves as a conventional diode. Okay, now if you look at the applications of tunnel diode, then as I mentioned, because of the negative resistance characteristic, tunnel diode can be used as a switch, amplifier and oscillator, and it has a fast response because of the narrow depletion region. It has a fast response, so it is used in the high frequency applications like microwave frequency applications. Okay, diodes are also used in oscillator circuit and FM receivers. Since it has a low current, so it is not used more at this point. Okay, so in today's class what we discuss? So we have discussed about one of the solid state semiconductor device, which is tunnel diode, and as I mentioned, tunnel diode is heavily doped diode, and because of the heavy doping, the width of the depletion layer is very narrow, and as the width of the depletion layer is very narrow, we can able to have a tunneling effect in this diode. Hence it is known as a tunneling diode or tunnel diode. Okay, and because of the tunneling of the charge carriers, we have the negative resistance characteristic in the characteristics of this diode. Okay, and if we look at the applications of diode, then it is widely used as a high frequency component as a oscillator and amplifier. सो आई होप कि आज के लेक्चर में जो हमने टनल डायोड के बारे में डिस्कस किया आपको समझ में आ गया होगा. लेट्स स्टॉप हियर. विल डिस्कस अदर एस्पेक्ट ऑफ दिस कोर्स in our next video lecture. Thank you very much.